The morning of December 18th, 1944. Snow covered the ground near the town of Manhay, Luxembourg, as a column of armour moved through the darkness. The lead tank in the German formation rolled forward steadily, its engine purring with a reliability that would have surprised anyone familiar with German armour of that period. The vehicle was an M4A3 Sherman, captured from American forces just days earlier during the opening stages of the Battle of the Bulge. Crewed by men of the 2nd SS Panzer Division, this American tank was about to demonstrate a truth that German engineers had been documenting for over a year. American tanks possessed something German manufacturers had never achieved: automotive excellence that simply refused to fail. The Sherman reached the American roadblock without incident. The defenders, hearing the familiar sound of one of their own tanks, held their fire. Behind this captured vehicle, the rest of the SS formation prepared to strike. Within minutes, the attack was underway, and the Germans seized Manhay using the Sherman as their lead element. This tactical deception worked precisely because of one undeniable fact. The Sherman's mechanical reliability was so consistent that even German crews, accustomed to equipment that broke down constantly, could depend on it to function when needed most. This single-night action encapsulated a bitter reality that German tank crews and engineers had confronted repeatedly since 1943. Every captured Sherman they drove, every American tank they tested, every kilometer they travelled in enemy vehicles revealed the same uncomfortable truth. The United States had solved fundamental problems in tank design that Germany never would. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story begins not with that December night in the Ardennes, but 18 months earlier, in the sands of Tunisia. February 1943 marked America's violent introduction to armoured warfare against the Wehrmacht. The 1st Armoured Division, green and untested, met Rommel's Afrika Korps and the 21st Panzer Division in battles that exposed every weakness in American tactical doctrine. At Sidi Bouzid and Kasserine Pass, American units suffered catastrophic losses. Inexperienced crews panicked under the hammer blows of German armour tactics perfected through years of combat. Tanks were abandoned, positions overrun, entire units shattered. For the Germans, these victories provided something more valuable than tactical success. They captured dozens of Sherman tanks, most abandoned intact by crews who fled in the chaos of battle. Among these prizes was an M4A3 Sherman designated USA 3067641, named War Daddy 2, belonging to Company G, 1st Armoured Regiment. The tank had been manufactured just 7 months earlier at Lima Locomotive Works in Ohio. It was nearly new, with fewer than 200 operating hours on its Continental R975 radial engine. Unlike most captured vehicles, which German units pressed immediately into service or cannibalized for spare parts, War Daddy 2 received special orders from the highest levels of the Wehrmacht. The tank was to be transported to Germany intact and fully operational for comprehensive testing at Kummersdorf, the Army's primary proving ground south of Berlin. Someone in the German High Command understood that studying American engineering might reveal insights more valuable than one additional tank in the desert. The journey from battlefield to test ground began with a challenge that would provide German crews their first shocking lesson about American automotive engineering. War Daddy 2 had to be driven 350 kilometers across North African terrain to the port of Sfax. Much of this route passed through areas still contested by Allied forces. German tanks regularly broke down after far shorter movements. The Panther tank, which would debut at Kursk later that year, could barely manage 150 kilometers without mechanical failure. The Tiger tank required railway transport for movements longer than 50 kilometers to preserve its fragile final drives and transmission. The Sherman was expected to fail somewhere along this route, confirming German assumptions about American mechanical inferiority. 4.5 days later, War Daddy 2 rolled into Sfax under its own power. The tank had covered 350 kilometers without a single mechanical failure. Lieutenant Klaus Schneider, the young officer who commanded the Sherman during its journey, filed a report that reached Albert Speer's office within weeks. His words were precise and professional, but they carried an undercurrent of disbelief. In 4 days of hard running across difficult terrain, this American tank required no repairs, no adjustments, no maintenance beyond checking oil levels and refueling. It started dependably every morning despite cold desert nights. The crew compartment remained comfortable even in midday heat. The controls were simpler than Germany's lightest tanks, yet the performance exceeded German medium tanks in operational consistency. The transmission shifted smoothly at any speed. The suspension absorbed terrain without damage. The engine ran quietly at all speeds. Schneider concluded his report with a statement that would echo through German technical circles. "I do not understand how the Americans build such machines." From Sfax, War Daddy 2 was loaded onto a cargo ship bound for Germany. The Army Weapons Office had issued explicit orders. This tank must reach Kummersdorf intact and operational. German intelligence had received fragmentary reports about American tank production, but seeing the physical vehicle made those statistics real, in ways numbers on paper never could. The Sherman represented mass production at a scale Germany could not match, built with automotive engineering principles Germany had not mastered. Spring 1943. The proving ground at Kummersdorf, Brandenburg. War Daddy 2 rolled off the transport rail car bearing the designation Beutefahrzeug 259, captured vehicle number 259, and German license plate WH058941. Test engineers had already stenciled armor, thickness measurements, and angles across every surface of the tank, marking it with precise notations for their comprehensive evaluation program. Kummersdorf, located 25 kilometers south of Berlin, served as the Wehrmacht's primary testing facility for both German and captured Allied equipment. Here, meticulous engineers measured, tested, and analyzed everything from track tension to transmission efficiency, documenting their findings in exhaustive technical reports that survive today in archives as primary sources, revealing what German professionals really thought about American equipment when freed to speak frankly. The Sherman was about to undergo the most comprehensive automotive examination German engineering could devise. German test engineers conducted the initial inspection with teams of specialists from multiple technical branches. They photographed every component from dozens of angles, measured every clearance with precision instruments, and documented construction techniques that seemed impossibly straightforward compared to German methods. The transmission caught immediate attention from powertrain specialists. Where German tanks employed straight-cut gears requiring precise tolerances and frequent maintenance, the Sherman used herringbone-cut gears that distributed stress across multiple teeth simultaneously. This design, standard in American automotive manufacturing since the 1930s, provided exceptional durability with minimal precision requirements. German engineers had considered herringbone gears too difficult to mass-produce given their industrial capabilities and workforce training. The Americans had been manufacturing them by the thousands. The testing began with basic automotive trials, designed to stress every mechanical system under controlled conditions. Engineers drove War Daddy 2 through obstacle courses designed to replicate battlefield conditions, measuring fuel consumption, monitoring engine temperatures, and recording transmission behavior under varying loads and terrain conditions. After each trial, they disassembled components to examine wear patterns, looking for signs of stress, inadequate lubrication, or design weaknesses. The results contradicted everything German tank doctrine had accepted about the necessary trade-offs between performance and reliability. The Sherman performed adequately in every category and excelled in the one metric German tanks consistently failed: operational endurance without maintenance intervention. The powertrain examination revealed design philosophy differences that explained much about American versus German approaches to armored vehicle engineering. The Sherman transmission featured 5 forward speeds plus 1 reverse, with synchronization in gears 2 through 5 that eliminated the need for double clutching during normal operations. This made the tank nearly as easy to drive as civilian automobiles, requiring minimal specialized training for drivers. German tankers, by contrast, spent considerable time learning complex double-clutching techniques and careful throttle management to avoid damaging their transmissions. The Sherman's design accepted that ordinary soldiers with basic automotive knowledge would operate these machines. German designs assumed highly trained specialists would always be available, an assumption that proved increasingly false as the war ground on and training time for replacement crews shrank from months to weeks. The Continental R975 radial engine. In War Daddy, 2 demonstrated remarkable tolerance for varied operating conditions. Engineers noted that the engine maintained consistent performance across temperature ranges that would have caused German engines to overheat or lose power. The cooling system, though simple in design, proved highly effective. The air filtration system handled desert sand without the frequent clogging that plagued German tanks in North Africa. Every system reflected a design philosophy that prioritized practical functionality over theoretical optimization. June 6th and 7th, 1943. The artillery range at Hillersleben. Reichsminister Albert Speer arrived to preside over a major armament conference attended by leaders from German industry and senior Wehrmacht officers. The demonstration program included hill climbing trials comparing German and captured Allied tanks. War Daddy 2 sat alongside the latest German designs, including a Panther Ausführung D fresh from production and a Ferdinand tank destroyer representing Germany's most advanced armoured fighting vehicle technology. Speer, responsible for German armaments production and personally accountable to Hitler for results, needed to understand what American industry could produce and how German designs measured against enemy equipment. The demonstration would provide answers neither Speer nor German tank designers wanted to acknowledge. The Sherman climbed the test slope smoothly. Its 5-speed synchronized transmission shifted without hesitation. Its engine maintained consistent power delivery throughout the ascent. The driver handled the vehicle with confidence, demonstrating the ease of operation that would become a Sherman hallmark. The Panther followed, its more powerful 700 horsepower Maybach HL 230 engine allowing it to match the Sherman's performance, but only barely and with considerably more difficulty. The driver needed expert skill with throttle and clutch to prevent stalling or transmission damage. The tank's final drives and steering mechanism required constant, careful management. The Ferdinand, massively heavy at 65 tons, struggled up the slope. Its electric transmission system, theoretically advanced, proved temperamental in practice. The vehicle demonstrated impressive engineering in concept, but revealed serious reliability issues in execution. What the demonstration at Hillersleben confirmed was not that the Sherman was superior in firepower or armor protection. The Panther clearly outmatched it in both categories. The Ferdinand's 88mm gun could destroy any Allied tank from ranges exceeding 2 kilometers. But neither German vehicle could match the Sherman's fundamental attribute. It worked consistently without specialized maintenance or expert handling. The engineers at Kummersdorf continued their exhaustive testing through the summer and fall of 1943. They drove War Daddy, 2,000s of kilometers across varied terrain. They operated it in extreme temperatures. They stressed every system to failure points. With each test, the same pattern emerged. The Sherman required minimal maintenance, tolerated operator error, and continued functioning under conditions that would have disabled German equipment. Reports from Kummersdorf began circulating through Wehrmacht technical circles, reaching tank commanders in the field and designers in factories. The language was professional and measured, but the implications were devastating. American industrial capability had produced a tank that German industry could not match in the one area that mattered most for sustained operations: reliability. This realization came at precisely the moment when Germany committed to production of the Panther and Tiger tanks, vehicles that embodied the opposite design philosophy. German designers pursued superior firepower and armor protection, accepting increased complexity, reduced reliability, and higher maintenance requirements as necessary trade-offs. They believed technical superiority could overcome material disadvantages and numerical inferiority. The testing at Kummersdorf proved they were wrong. The mathematics of mechanized warfare were brutally simple. A tank that functioned when needed was infinitely more valuable than a tank that possessed superior specifications but broke down before engaging the enemy. A tank battalion with 80% of its vehicles operational could execute missions that a battalion with 40% operational vehicles simply could not attempt. Reliability wasn't a secondary consideration. It was the foundation of operational effectiveness. By mid-1943, German engineers at Kummersdorf had documented these findings with scientific rigor. They understood American advantages. They reached correct conclusions about the strategic implications. But understanding a problem and solving it are fundamentally different challenges. German industry lacked the capacity to retool production around reliability principles, while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. The M4A3 Sherman variant, powered by the Ford GAA Vate engine, represented the pinnacle of American automotive engineering applied to military requirements. Ford had developed this engine from an experimental 12-cylinder aircraft power plant, reducing it to 8 cylinders to create what would become the preferred American tank engine of the war. The 18-litre all-aluminum engine produced 450 horsepower at 2,600 RPM, delivering over 1,000 pound-feet of torque from idle to 2,200 RPM. The GAA featured advanced engineering, rarely seen even in modern engines: dual overhead cams, 4 valves per cylinder, gear-driven accessories eliminating belts and chains, dual ignition with twin spark plugs per cylinder. Everything about its design emphasized durability, ease of maintenance. German engineers examining captured M4A3 tanks found an engine that surpassed their own vaunted Maybach HL 230 in nearly every practical measure. Reliability testing, conducted by American forces in winter and spring 1944, demonstrated what German crews already knew from field experience. One M4A3 travelled 2,097 miles over 203 hours without mechanical failure. By contrast, a standard M4 broke down after just 15 hours. An M4A1 lasted 27 hours. The M4A3's superiority in operational endurance was not marginal, it was decisive. German tank crews who captured and operated M4A3 Shermans during 1944 and 45 discovered these advantages firsthand. The tanks were so reliable that German commanders preferred them for recovery vehicles, knowing they would function when needed to tow disabled Panthers and Tigers. The irony was bitter. German crews used American tanks to rescue German vehicles that had broken down with depressing regularity. Documents from German heavy tank battalions in Italy note with frustration how captured Shermans converted to armoured recovery vehicles outperformed purpose-built German recovery equipment. The Bulge Panther, Germany's Panther-based recovery vehicle, broke down almost as frequently as the tanks it was meant to recover. Sherman-based recovery vehicles simply worked, day after day, mission after mission. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The contrast between design philosophies became increasingly stark as the war progressed. German tank development from 1943 onward prioritized ever heavier armor and more powerful guns. The Tiger II, introduced in 1944, weighed 70 tons and mounted an 88mm gun capable of destroying any Allied tank at extreme range. It was also mechanically unreliable, difficult to transport, and nearly impossible to maintain in field conditions. Production figures tell the strategic story with brutal clarity. The United States produced approximately 50,000 Sherman tanks of all variants. Germany produced roughly 6,000 Panthers and fewer than 2,000 Tigers combined. This disparity was not primarily about industrial capacity, though American manufacturing advantages were enormous. It reflected fundamental differences in design, philosophy, and production priorities. American designers created a tank that could be mass-produced by automobile factories using existing manufacturing techniques and trained by automotive workers with minimal specialized skills. The Sherman's components were standardized, interchangeable, and repairable in field conditions by mechanics with basic training. Spare parts were abundant because the powertrain shared components with other vehicles and utilized automotive-grade materials that American industry produced in vast quantities. German designers created tanks that required specialized factories, skilled craftsmen, and extended production time per vehicle. Panther and Tiger components demanded precision manufacturing beyond normal automotive tolerances. Assembly required experienced workers capable of complex fitting and adjustment. Field repairs needed specialized tools and parts that were always in short supply. The logistics system to support these vehicles collapsed under its own complexity. The operational consequences of this reliability gap manifested across every theatre where German and American armour met. In Normandy, during the summer of 1944, American armoured divisions maintained operational readiness rates above 70%, despite intensive combat. German Panzer divisions struggled to keep 40% of their tanks functional. Mechanical breakdowns removed more German tanks from action than Allied firepower. After action, reports from American tank battalions document encounters where German Panthers and Tigers withdrew from advantageous positions, not because of tactical pressure, but because their vehicles were breaking down. Crews abandoned tanks with seized transmissions, failed final drives, overheated engines. German units left trails of disabled vehicles across the French countryside, each one representing not just a tactical loss, but a strategic failure of engineering philosophy. The Battle of the Bulge in December 1944 exposed these problems with devastating clarity. Germany's last major offensive in the West depended on rapid armoured thrusts to seize key objectives before American forces could respond. The operation required German armour to cover significant distances quickly and maintain combat effectiveness over extended periods. Panthers and Tigers broke down with appalling frequency during the offensive's opening days. Units that began the attack at full strength watched their operational vehicle counts decline, not primarily from combat losses, but from mechanical failures. Final drives snapped under stress. Transmissions seized from inadequate lubrication. Engines failed from overheating or oil starvation. By the offensive's second week, many German armoured units were combat ineffective not because they'd been destroyed in battle, but because their vehicles simply stopped working. American armour, by contrast, maintained remarkable operational readiness throughout the battle. Sherman tanks that had been in continuous service since the Normandy invasion 6 months earlier kept functioning. They required maintenance, certainly, but that maintenance could be performed by ordinary mechanics using standard tools and readily available parts. The logistics system supporting American armour worked smoothly because it had been designed around realistic maintenance requirements and achievable supply needs. German crews who captured Shermans during the Bulge discovered what their counterparts in Tunisia had learned 18 months earlier. American tanks worked. The 2nd SS Panzer Division's use of captured Shermans at Manhay on Christmas Eve 1944 demonstrated both tactical ingenuity and bitter acknowledgement. German commanders used enemy vehicles because they were more reliable than their own equipment. The 150th Panzer Brigade, formed specifically for Operation Greif, Otto Skorzeny's commando operation to sow confusion behind American lines, incorporated captured American vehicles, including Shermans, precisely because they could be depended upon to function during critical missions. When German special forces needed vehicles that absolutely would not break down at the worst possible moment, they chose American equipment. This preference for captured American armour extended across German armoured units wherever Shermans were available. The 10th SS Panzer Division maintained a separate unit of 10 Shermans. Multiple German divisions formed captured tank companies, incorporating American vehicles. Intelligence reports document dozens of Shermans in German service, all marked with German crosses, all valued for their reliability. The testimony of German tank crews who operated Shermans is remarkably consistent. The vehicles were easy to drive, comfortable for crews, mechanically reliable, and simple to maintain. German tankers accustomed to Panthers that demanded constant expert attention, Tigers that required specialized maintenance after every mission, found the Sherman's automotive simplicity almost incomprehensible. Otto Carius, one of Germany's most successful tank commanders, acknowledged in post-war interviews that the Tiger was mechanically unreliable and difficult to keep operational. He noted that American and British tankers rarely faced German heavy tanks in combat, not because Tigers avoided battle, but because so few were actually operational at any given time. Most Tigers were, in maintenance, awaiting parts, or broken down. The strategic implications of this reliability gap extended far beyond individual tank versus tank encounters. Modern mechanized warfare required sustained operational tempo over extended campaigns. Armies needed to move quickly, maintain pressure on enemies, and exploit breakthroughs before opponents could react. All of this demanded vehicles that functioned consistently over thousands of kilometers and months of operations. American armor could sustain this operational tempo. German armor could not. The mathematics were brutal and decisive. An American armored division could execute missions requiring hundreds of kilometers of movement and weeks of continuous operations because 70 to 80% of its tanks would be functional throughout. A German Panzer Division, attempting the same mission, would see its operational strength decline to 30 or 40% within days, not primarily from combat losses, but from mechanical breakdowns. This operational limitation constrained German tactical options and strategic planning. Commanders could not rely on their armor to be where it was needed when it was needed. Offensive operations had to account for the certainty that significant numbers of tanks would break down en route to objectives. Defensive deployments required keeping substantial reserves of vehicles in maintenance status. The entire operational calculus of German armored warfare was compromised by fundamental unreliability. American commanders faced no such constraints. They could plan operations confident that their armor would arrive at designated locations approximately on schedule and in approximately projected strength. This reliability enabled the operational flexibility that characterized American armored doctrine. Task forces could be formed, dispatched on independent missions, and counted on to accomplish objectives because the vehicles would function. The contrast between German and American tank recovery and maintenance systems illustrated deeper institutional differences. The American system was designed around realistic acknowledgement that vehicles would require regular maintenance and occasional repairs. Recovery vehicles were abundant, spare parts plentiful, mechanics trained on standardized procedures that worked across all Sherman variants. The German system assumed that tanks would function reliably if operated by skilled crews and maintained by expert mechanics. This assumption proved catastrophically false. German recovery and maintenance capabilities were never adequate for the actual breakdown rates of Panthers and Tigers. Units waiting for spare parts, specialized tools, or trained mechanics to arrive could wait weeks. Disabled vehicles accumulated faster than they could be repaired. Post-war analysis by American and British intelligence organizations confirmed what German testing at Kummersdorf had revealed in 1943. Systematic examination of destroyed German tanks found mechanical failures as common as combat damage as causes of loss. Final drives broken from stress, transmissions seized from inadequate lubrication or operator error, engines burned out from overheating or oil starvation. The German obsession with individual vehicle superiority and impressive specifications had blinded them to the critical importance of reliability and maintainability. They built tanks that no conscript mechanic could maintain without extensive specialized training, powered by engines that demanded constant expert attention from skilled technicians, supported by a logistics system that collapsed under the accumulated strain of supplying countless unique parts to scattered units. The lessons learned through testing at Kummersdorf directly influenced German tank design thinking in the post-war Bundeswehr of West Germany. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American automotive engineering principles and deliberately applied them to military vehicle development. The resulting Leopard 1 incorporated many design philosophies that had made the Sherman successful. Robust powertrain with substantial design margins, easy maintenance requiring minimal specialized tools, standardized components enabling rapid field repairs, growth potential allowing future upgrades without complete redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. German engineers had finally learned the lesson that War Daddy II and dozens of other captured Shermans had taught at Kummersdorf. Industrial maturity and sound engineering principles based on practical experience mattered more than theoretical, technical innovation pursued without regard to manufacturing reality. The reliability gap between Sherman and German tanks influenced not just tactical armored warfare, but fundamentally shaped broader understanding of military industrial capacity and its decisive role in modern conflict. Germany entered World War II with technical advantages in many weapons systems, possessing scientific knowledge and engineering expertise that exceeded most opponents. However, Germany lacked the industrial depth and manufacturing sophistication to maintain those advantages through sustained mass production while simultaneously fighting enemies on multiple fronts. The United States entered the war with weapons that were less technically sophisticated in many respects, but possessed industrial capacity to manufacture them in overwhelming quantities while continuously improving quality, reliability, and performance based on combat feedback. This industrial approach, perfectly exemplified by Sherman tank design and production, proved far more effective than German technical sophistication applied to small-scale production. The United States produced nearly as many Sherman tanks as Germany produced tanks of all types combined, while also producing enormous quantities of every other weapon type, supplying allies through Lend-Lease, and maintaining the highest standard of living among all combatant nations. This economic performance, impossible for Germany to match even before strategic bombing intensified, decided the war's outcome as certainly as any battle. The mathematics were simple and brutally clear when examined objectively. A Sherman with a 75mm gun that reliably reached the battlefield and fought effectively was infinitely more valuable than a Panther with a superior gun that broke down before engaging the enemy or required 3 days of maintenance for every day of operations. A tank battalion with 80% of its vehicles operational could execute missions that a battalion with 40% operational vehicles simply could not attempt. German tanks consistently failed this fundamental test throughout the war. American tanks consistently passed it. Kummersdorf testing had proven this beyond reasonable doubt by mid-1943, even as German commanders continued deploying Panthers and Tigers that looked fearsome and possessed impressive specifications, but couldn't be relied upon to function when needed most. The Sherman tank didn't win World War II through technical superiority in firepower or armor protection. It won through industrial superiority expressed as mechanical reliability, consistent availability, and ease of maintenance. German engineers at Kummersdorf understood this by mid-1943 based on their exhaustive testing. They wrote detailed reports documenting their findings. They tested the evidence repeatedly with scientific rigor. They reached correct conclusions about American advantages. But understanding a problem and solving it are fundamentally different challenges. German industry lacked capacity to retool production around reliability principles, while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its civilian automotive sector over decades of commercial competition and simply extended those mature principles to military production with remarkable success. The captured M4A3 Sherman tanks that German crews drove hundreds of miles without mechanical failure. The Sherman's German engineers tested exhaustively at Kummersdorf and other proving grounds. The American tanks that German recovery units preferred because they actually worked when needed all told the same story. Every kilometer driven without failure was evidence that German tank design had taken a fundamentally wrong path by prioritizing specifications over reliability. Every test demonstrating American automotive excellence was proof that industrial maturity and practical manufacturing experience mattered more than theoretical performance calculations. Every comparison between Sherman and German tank reliability proved that Americans had solved problems German engineers didn't realize they needed to solve until it was too late to matter. The strategic lesson transcended tanks and warfare, offering insights for any complex endeavor requiring sustained performance under demanding conditions. In engineering, in business, in military operations, operational consistency often matters more than peak performance. The best design is frequently the one that functions effectively when needed, not necessarily the one with the most impressive specifications on paper. The Sherman and its German contemporaries provided an enduring lesson that remains relevant 8 decades later. German tanks were engineering marvels that spent too much time broken down. American tanks were competent machines that kept working. In sustained industrial conflict, consistent adequacy defeats intermittent excellence. The Germans learned this lesson at tremendous cost. Their testing of captured Shermans gave them empirical data and technical analysis to understand precisely where their approach fell short. But understanding a problem and possessing the capability to solve it are different challenges. Germany could not solve its tank production and operational problems within the constraints of wartime industry, limited resources, and competing priorities. The knowledge became an exercise in frustration, knowing what was needed but unable to achieve it. The testing at Kummersdorf represented a road not taken, a glimpse of an alternative approach that might have altered outcomes. If Germany had prioritized dependability and producibility from the beginning, if designers had been free to create simpler vehicles, if production had focused on adequate machines in large quantities rather than technically sophisticated vehicles in small numbers, perhaps the course of events might have been different. But this is counterfactual speculation. The decisions that led to Panther and Tiger development were based on Germany's actual industrial capabilities, strategic situation, military culture, and political leadership. Those decisions produced tanks that performed brilliantly in isolated combat engagements, but failed strategically. The Sherman succeeded strategically, despite tactical limitations. For students of World War II and military history, the story of captured Shermans in German hands offers profound insights beyond the usual narratives of tank versus tank combat. It reveals the critical importance of logistics, maintenance, and industrial production in modern warfare. It demonstrates how engineering approaches reflect and shape national character and industrial capability. It proves that technical sophistication without operational consistency is ultimately hollow achievement, failing under the pressures of sustained industrial conflict. The engineers at Kummersdorf, who spent months testing War Daddy II and other captured American vehicles, produced some of the most honest and insightful technical analysis of the entire war. Their reports survive in archives as primary sources revealing what German professionals really thought about American equipment when freed to speak frankly in technical documents rather than propaganda. These reports are remarkable for their objectivity and clear recognition of American strengths. The conclusions documented across hundreds of pages were inescapable. America had developed a tank Germany could not match in operational consistency and producibility, and those particular factors mattered more strategically than the technical superiority German designs achieved in firepower and armor protection. War Daddy II, that single M4A3 Sherman captured in Tunisia and tested exhaustively at Germany's premier proving ground, became an enduring symbol of this realization. One tank among 50,000 produced, yet revealing truths German engineers had to confront professionally, even as commanders and political leaders chose to ignore them or proved unable to address them. The Americans had achieved in tank production what Germany demonstrably could not. Not through superior metallurgy, not through secret technology, not through revolutionary innovations, but simply through superior engineering approach, better industrial organization, and clear-headed prioritization of dependability over performance specifications alone. The tank that never broke down defeated the tanks that too often did. The straightforward, maintainable workhorse achieved strategic victory that perfect engineering could not deliver. Mass-produced adequacy triumphed over limited production excellence. These were not the lessons Germany wanted to learn, but they were the lessons that mattered. In the end, the German testing of captured Shermans represents one of the war's most significant moments of technical truth. Professional engineers evaluated enemy equipment with scientific objectivity and reached unavoidable conclusions. The American approach to tank design was strategically superior for modern industrial warfare. Not superior in firepower, not superior in armor protection, but decisively superior in the factors that actually determined strategic outcomes: production capacity, operational dependability, field maintainability, and sustained availability. These weren't glamorous attributes that inspired propaganda or stirred patriotic fervor. They didn't generate the awe surrounding Germany's mighty tigers or powerful panthers, but they won the war decisively. The engineers at Kummersdorf knew this truth. Their reports documented it explicitly. But their knowledge came too late to change German outcomes, and probably could not have changed them even if recognized earlier, given the constraints Germany faced. The captured Shermans tested at Kummersdorf stand as monuments to an eternal principle of engineering and warfare. Operational consistency consistently trumps peak performance. Simplicity usually beats complexity in sustained operations. Steady adequacy always defeats intermittent excellence over the course of extended campaigns. The Germans built tanks that were unquestionable engineering marvels, technological triumphs that impressed everyone who examined them. The Americans built tanks that won the war decisively. The testing at Kummersdorf documented precisely why, in reports that remain powerfully instructive 8 decades later. This is the enduring legacy of those captured American tanks and the profound lessons German engineers learned from vehicles that simply refused to break down. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.